So today we're going to do section 8, where we're going to talk about applications of conditional probability. So as we talk about that, notice there at the top it says conditional probability can help us understand real life situations. We will examine a few of them during this lesson. We will use two-way tables, though not always hypothetical 1,000 two-way tables, to analyze the evidence. We will also begin using tree diagrams. Well, I'm actually going to leave out the tree diagrams. We're just going to focus on hypothetical tables and two-way tables and Venn diagrams, okay, in this course. But tree diagrams are helpful. I'll just say that for your statistics course. So, opening activity here, innocent or guilty. A certain teacher, Mr. L.I. Detector, it claims that he can tell when students are lying about cheating on their homework. This is true. Unfortunately, he also accuses some students of telling the truth. Does that make sense? So he can always detect a liar, but he doesn't always get the people that are telling the truth correct. So what are the chances that someone who is accused is actually telling the truth? You can investigate this question through a practical experiment. You will need a 6-sided die, which I'm going to just go ahead and tell you that I rolled the die on your behalf. And suppose you know that every student who lies about his or her homework is accused, and that 1/6 of the students who are not lying, so that'd be telling the truth, about their homework are still accused of lying, and that 1/6 of your classmates are lying about their homework. Okay, 2. First, investigate what happens for one student. So what we're going to do is we're going to roll a die. So, and notice I have it's already completed below. Okay, and so if it is a 6, then the student is lying and accused. Mark lying, yes. If it is any other number, mark lying, no. So notice here, I'm going to start looking at this table below, and let me do this. I think, so basically, oh, that's too big. That's too small. So basically, this table here, like I'm emptying all these sections. It's supposed to be emptied out here. Do you get the idea? Are you okay with that? So it's supposed to be empty, and we're going to roll a die, and we're going to try and figure out if they are lying, right? And so notice here it says if it is a 6, right? When you roll a die, then the student is lying and accused. So mark lying, yes. Okay. If it is any other number, mark lying, no. So the first time, let's just say I roll a dice and I get a 5, right? And so, boom, that's a no, right? Get the idea? The next time I roll a 3, that's not a 6, so that should be, a no. Okay, the next time I roll a 1, it's a no. The next time I roll a 6, it's a yes. Are you guys okay with that? Can I just uncover the rest of them and so you get the idea? The only time it's a yes is if they roll a 6. So I'll pull these back here. Okay. Now, it says in the second thing. It says, we know Mr. Lie detector can always spot a liar, so mark yes in lying with a yes in accused. So anytime we marked a yes, right, in lying, like in this one, then we're going to have to mark it as a yes in the accused. Okay, so that one and this one. So how are we going to fill in the rest of those? Do you get when we're, okay, do you guys understand that? Yeah? Okay, so then how am I going to get the rest? Well, it says here in step 3, right? Now let's see who is accused by Mr. Lie detector, but is not lying, because, right, we know that if they are lying, that they get accused, right? So now we're at the people that are not lying, and we want to see of these people that are not lying, who is still accused, who does he still accuse of lying, right? So even though they're being truthful. And so they want us to roll the die again, right, for each no. Okay, and if you get a 6, then Mr. Lie detector makes an accusation against that student. So mark yes in the accused. For any other number, no accusation is marked, so mark no. Okay, so and you're going to do that 36 times, right? So the first time I roll the die and I got a 6. Okay, so I'm going to mark yes. So the person is not lying, but Lie detector will accuse him. The next time I roll a 1, so that means that he's not accused. The next time I roll a 6. Whoops, sorry. So he is accused. I could skip 4 because we know that if a person is lying, that they are always accused. And for 5, I know that I rolled a 1, and so I got a no. Okay, do you get the idea of how to fill in the second row? So can I just go ahead and uncover the rest of these? Whoops. Okay, how are we doing? Good? Okay, so I know I'm going to have to collect some data here. So let's do this. Let's mark where the person is lying. So we have here, right? Let me get back to my nice and thick. So they're lying there. And we know here, right, that the person's a liar. So every time I have a yes in the top, right, I want to highlight in yellow. I only have 1 in that one. And then here, and here. And then finally here. And then let's mark all the times where the person is not lying but is accused of lying. So instead of doing the whole thing, I'll just mark the yeses that are still yeses in the bottom. Okay, do you get the idea? So I've got those covered here, so let's go on to the next page. So we're going to fill in this table. We do know that we did it 36 times, so that's why there's a 36 down here. So now what I want to do is I want to go up and figure out some of my things that I know. So when when I highlighted yellow, that means they were lying and they were accused, right? So how many times were they lying and accused? Well, I see that I have, let's see here. So 1, 2, 3, 4, 5, and 6 times. So I'm going to put a 6 in lying and accused. So I'm going to come down here. Lying and accused is this box right here. And I'm going to write a 6 in there. That's way too big. That's way too big. Let's do this one. There we go. Okay, and then let's go back and figure out the number of times that they were not lying, but they were accused. So I know I have 1 time here, 2, 3, 4, 5, and 6. That's 1, 2, 3. Okay, do you guys see it? So there were 6 times that they were not lying, but were accused. So I'm going to come here, not lying and accused. Not lying and accused. Oh, that's this one here, isn't it? So we know that is 6. And we know 6 plus 6 is 12. And then I know that to add to 36, this has to be a 24 in this one, right? Because we know these two have to add together to get the 36. Can I fill in anything else about my information? Not accused and lying. Oh, how can we fill in not accused and lying? That's a really good one, actually. He always gets that right. If they're lying, they're accused, right? So we know this has to be 0, right? So maybe let's just draw a little note here, right? If lying, they are accused. I forgot about that fact, so I'm appreciating that right now. So then I can add going down and get 6 here. I know this has to be 24 that are not lying and not accused. And then if I add going down there, that's 30. And then you can see that if I add the totals across this way, that it does equal 36 also. Okay. Were you guys surprised by the results? No? Yeah, I wasn't either. I think that the data mimics what the probability really well. So I would just say no. Data mimics the probability. Right, described. How do they compare with what you expected? I'm just going to draw an arrow here because let's go see. What proportion of truthful students are accused, sorry. So what is the probability of a truthful student being accused? So notice here that we have a given in the problem, right? Truthful students. So we're looking for accused. So we're looking for the probability, right, that they are accused given that they are truthful. How is truthful represented in our chart, you guys? How is truthful represented in our chart? Not lying, okay? Sorry about that. So remember, when you have a given like that, that we're going to focus on just a specific portion of the whole chart, right? So the given tells me that we're going to focus on the not lying section, which is this column. So how many in that column are accused? 6. And how many are there total in that column? Because remember, when I have a given, you're just focused on that column, okay? So you're not going to use the grand total, you're just going to use the total for the column. And then 6/30, well, that reduces to be 1/5, which is exactly 0.20, right? That's 20%. Okay, now notice it says, what proportion of accused students are telling the truth? Okay, and again in this one, right, so it's what proportion of accused students are telling the truth. So here's a given again. So this time, instead of looking at a column, we're going to look at a row because accused is a row in this chart. So we're going to look here just at this row. And we're looking for the probability that they are telling the truth, right, or truthful, given that they are accused. Now, we already said, right, based on, right, truth is not in the table, but not lying is. So if we're going to look for the probability of someone lying in that row, you can see that there are 6 of them that are lying, not lying. How many? Oh, it is 6 though. 6 are not lying. And so I was looking at the wrong one, but it was the same number. Okay, so there are 6 students, right, that are not lying in that row. And then how many total are there? 12. Well, we know that reduces to be a half, and that's 0. Right, 5 or 0.50 if I put an extra decimal in there. Okay, is the probability that a truthful student is accused the same as the probability of an accused student is telling the truth? Is the probability that a truthful student is accused the same as the probability that an accused student is telling the truth? So are they the same? Basically, we're comparing our answers here, right? Are these the same? And the answer is no, right? The probabilities are not the same. Right? So think about it. One is the scenario, right, where they're telling the truth, right? We're looking to see of the students that are telling the truth, how many of them will be accused. That would be 20% of them, right? And then the second one is of those who are accused, how many are telling the truth? 50%. It's just a little bit different, right? So the first one, we know that they're telling the truth. So we're seeing how many of those, what percent get accused. And then the second one, we know they're accused. So we're trying to figure out, well, how many of them would be telling the truth? Okay. Now it says, let's use the theoretical probability to fill in the table below. Okay. So notice here, we're using theoretical probability right now. So what were we using up above? We weren't using theoretical. What's the other one called? Empirical. There you go. I was coming up with experimental in my head. I was like, oh, it's empirical, right? But it is that idea of experimental where you are pulling out from actual data, right? And now this is theoretical. So based on what you would expect in theory. So, um, so we can fill in specific things right away in this chart. And let's do that. So the first thing we do know is that we know all liars are accused. So therefore, right, this is the big part here. We know no liars are not no liars are not are not accused. So that means that this has to be a 0 right here. Are you guys okay with that? The other one that we can do right away is this one right here. Because we know, remember we rolled a die and it was 1 and 6, right? It was when you roll a 6, so it's a 1 and 6. We're going to be liars, so we know that. I'll put a 2 here. 1/6 of the total are liars. So I know that 1/6 of the 36 is 6. Okay, so the next one that I could do this one now, can't I? Because don't the top two have to add to be 6? So doesn't it mean the top one has to be a 6 here? And then the next one that would be easy to do, right? And you can obviously flip-flop 3 and 4 is this one, number 4, because we know that when you add, what do you add to 6 to get 36, right? Well, what do you add to 6 to get 36? 30. Okay, so the next one that we can do is going to be this one here. I'll label this 5. I'll put it up here too. So 5. 1/6 of all not liars are accused. Yeah, I can spell liars. There we are. Remember, once we discovered who was lying and not lying, right, in the top column when we were rolling the die, right? And then anyone that was lying, they got an automatic accused because he gets those 100% of the time. So then we had to roll the die a second time, right? For those that were not, who were not lying, who were telling the truth. So if it were rolled a 6, then we know that they were not lying and accused, right? And so that means that was a 1 in 6 chance because there's 6 sides to the die. There was only one option, right? The 6. And so there was a 1 in 6 chance. So 1/6 of all not liars are accused? Well, that would be 1/6 of 30, which is 5. By the way, this here was 1/6 of 36, which was 6. Okay, are we good with that? Because then we can figure out this one here, right? Because we know that if we were to add the top two, it has to be 30. So 5 plus what gives me 30? Isn't this 25? And then we can figure out this one here, because the rows have to add up. So 6 plus 5 was equal to 11. So I can put 11 over here. And then finally, the last one, this will be my 8th one. And so we know 0 plus 25 gives me 25. And you can see that it all adds up nicely. Are you okay with how we filled that in theoretically? Right? It's a good reminder of how to do theoretical versus empirical, right? Okay, what proportion of truthful students are accused? Okay, so what proportion of truthful students are accused? So we're doing it again, but we're doing it with the theoretical data. So here's my given. I'm going to go ahead and do it in blue again. So what is the probability, right, that they are accused given that they were truthful? And again, truthful means not lying, right? I'll just say not lie. So that means we are only looking at the not lying column here. And you can see that would give me, there are 5 that are accused in that column out of the 30, which is a 1 in 6, which is approximately 0.167. What proportion of accused students are actually telling the truth? So again, our given proportion of accused students, there's my given, are actually telling the truth. So this time I'm going to find the probability that they are telling the truth given they were accused. Okay, so looking back up here, right, we're accused. We're just going to look at this row here that I have highlighted in green. And so notice on this one, those that are telling the truth, again, telling the truth is not lie. So the not lying is 5. And the total for that row is 11. So 5/11ths, which that is approximately 0.455. Notice that if we compare that with our other results, right? Let me see if I can get this here. I can see it. Right? The probability of accused, given that they were truthful, right? 0.20 was what we got empirically, and theoretically it should have been a little smaller, about 0.167. Not too bad though, right? It's fairly close considering our small sample size. And the same thing for the other one, right? The empirical that we got was the 0.50, whereas the theoretical is 0.455. Okay, are we all good? Sweet, let's move on. Exploration number 1. Measles means spots, but do spots mean measles? That's the question we're going to explore. It says 6. Aaliyah has measles. She also has red spots. Ben has red spots. Does he also have measles? So this is the question we want to try and answer. So let's go to question 7. It says, in 2008, there were approximately 12 million children under 16 in the UK, and about 1,200 of them got the measles. Suppose 99% of the children who have measles also have red spots. Okay, so then it says, what's the probability someone who has spots has measles? Well, let's take a look at information that they've given us. 1, did you notice that they have 12 million children, and that's the total here in our 2A table. So it's not going to be 1,000 2A table. It's going to be a 12 million 2A table, right? But it's good. It's a nice big sample. The next piece of information that they give me is that about 1,200 or 1,200 got the measles. Okay, so got the measles, that's going to be this total right here. So I'm going to use the color to kind of highlight where I'm putting things. And you can see that I have 1,200 here. So I can fill in this box, so I might as well do that. 1,200 from 12 million gives me 11,998,800. They did give me one other piece of information. It says, suppose that 99% of the children who have measles also had spots. Okay. Oops, that's not the color I want. I want to use this color. Okay. Okay, well, so now this time that's not like the number of children. It's a percent this time, and we're not filling in percents, we're filling in numbers. So what we're going to do here is I'm going to come and take this information, and it's 99%. So I'll do 0.99 and then multiply that by, those are of the children who have measles also have spots. So we're only looking at the number of children that have measles. That's that 1,200 or the 1,200. And when you multiply those together, you get 1,188. So where is that going to go in our chart? Well, that's have measles and have spots. So that's going to be this cell right here, first cell. So this is 1,188. Well, that gives me some good information. So I do know that if they add going down, right, I should get the 1,200. So that means in the cell right below it that I should have 12. 12 have measles but don't have spots. Can I fill out any other information? Not at this point, right? So let's look at A. That's all the information I can fill out. Part A says, what is the probability that someone has spots, has measles? So this is a given, right? The given is that someone who has spots, right, is your given, has measles, so we're going to be looking for the probability, right, of measles given that they have spots. So if we're looking at that, if they have spots as the given, that means we're looking at this row right here. Uh-oh. We can't do it, can we? If it was the other way around, right? Probability of someone having spots given they have measles. Well, we have that, right? Because we have the whole column, right? But we don't have the whole row's information. So we don't have enough information, do we? So there's not enough info. I'm going to say here until part B, because then we're doing part B next, and we're going to be able to fill in more information. Okay, fine. Part B. Clearly, measles isn't the only condition that causes spots. Suppose 10%, okay, here, hang on. Suppose 10% of children under 16 have spots. Put the figures in the table below to show the total number of people in each row and column. We're using 12 million in this example instead of 1,000. Well, okay, so 10% of children under 16 have spots. Okay, so 10%, again, they're using a decimal, so we have to come up with, this is of the total, that's of the 12 million. Isn't that 1,200,000 then? Notice that's going to be this column here, right? Okay, and now once we have that, we can fill in the rest of the information. Okay, so like I can figure out this cell right here because I know that the 1,200,000 plus something has to equal 12,000. So from the 12 million minus that 1,200,000 is 10,800,000. Okay, and I do know that this 1,188 plus something has to be equal to that 1,200,000. Well, I'll subtract that 1,188 from the 1,200,000, and when I do that, I'll get 1,198,812. And then the same thing with the next row. The 12 plus something has to be equal to 10,800,000, and I'll just tell you that this is 10,799,988. Are we okay with that? Yeah? Okay. Now it says, let S be the event that a child has spots, and S to the C, right? That looks like a C power. Now, this is saying not C, or the complement of C, right? The complement of C. So that would be the event that he does not have spots, right? So M would be that the child has measles, and then the complement of M, that's what M to the C would be, right? The complement of M would be that a child does not have measles. Got it? So that little c that is given up here, right, that just is talking about the complement of S. Okay, so express each event that we have here below using your trees or your table to calculate. We're just going to use a table. So what does this first one represent here? Well, remember M stands for measles, S stands for spots, and the C means complement, right? So if I were to put this one here in words, we're finding the probability okay, of measles, right, that's the M, given, what's the S to the C? That's the complement of spots. The complement of spots would be no spots. Okay, so we're finding quite a few here. It'll be hard to focus. Let's do this. Actually, I'll highlight it and then I'll release the highlighting. So the given of this next one is that they have no spots. Well, no spots is a row. So we're only looking at this row right here. Do you guys agree? So, what's the probability of having measles in that row? Well, the probability of having measles is 12, right, out of, then the total for that row, which is that 10,800,000. Now, on this one, okay, we're going to go a lot. Usually we only go 3 decimal places, but notice how small this number is. There'll be, when you divide those, you'll have 5 zeros, 4, 5, followed by a 1. So if you don't have spots, it's very likely you don't have measles. I mean, look how small that percent is. Got it? Let's take a look at the next one and let's interpret what this one means. I'm going to delete the row that I have, this highlighting that I have here. And let's take a look now at the next one. So this next one, right, this is the probability, okay, of S given M. Well, S is spots, so what's the probability of having spots given that they have measles? So now we know they have measles, so what's the probability that they have spots? Well, if the given is measles, that means we're going to look at this column alone here, right? So in that column, how many people have spots? Well, it's the 1,188, and then we're going to divide that by the 1,200, 1,200. And when you stick that on your calculator, you get 0.99. So 99% of those that have measles will have spots. Is that clear? Kind of a cool way to look at the data, right? Okay, so let's go to the next one. I'll go ahead and I'll delete my highlighting there. Here's a good question. Let's just focus here on writing it first in words. So probability of M given S. Oh, they flipped the M and the S from the last one, haven't they? So what are we finding the probability this time? Measles. Given they have spots. So the given is spots. So I'm going to look in my chart here. Spots is this row right here that I'm highlighting. And so we are looking for what is the probability that they have measles. Well, in that row, 1,188 of them have the measles, right? And the total for that row is the 1,200,000. When you stick that on your calculator, you're going to get 0.00099. Okay, I went to a bunch of decimal places here. So if we have someone that has spots in front of us, the probability that it's measles is all the way down there, right? It's less than a tenth of a percent, just under a tenth of a percent. That's really small, isn't it? Okay, let's take a look at the last one. Let's define what the probability is, and then we'll look at the table. So this is the probability. Probability of, and then it's SC given MC, or the complement of S given the complement of M, right? Well, the complement of S is no spots, right? Because S is spots. So the complement would be no spots given the complement of M. M is measles, so that would be no measles. Okay, so fine. If we're given no measles, that means we're looking at this column here. And how many in that column have no spots? What's the 10 million? 799,988. And then that's divided by the total of that column, which is the 11,998,800. And when you put that on your calculator, I'm just going to tell you it's 0.900089. So there's a 90% probability that a person who does not have measles will not have spots. Get rid of that highlighting. Okay. Are we okay with that? So what is the probability that Ben has measles? Okay, now when we answer this, right, you have to remember at the very, very beginning that Ben has spots. Do you guys remember that? So I'm going to take this information all the way down here, and I'm going to say, remember, it's given that Ben has spots. So isn't this the probability, right? That Ben has measles given that he has spots. Do you see it? Wait, didn't we already figure that out? We did up here, didn't we? That was part C. not part C. Which one is it? Oh, part C. Sorry, I was looking. So this would be equal to 0.00099. So it's less than 0.1% that he has measles if he has spots. How are we doing? Can I move on to the last page? Okay. This is a good discussion. Part of me wants to cut it out because of time, but it is a good example. So it says here, HIV testing. How believable are test results? And it says the ELISA, and it's an acronym, enzyme-linked immunosorbent assay tests, can be used to detect whether a person has certain conditions, such as being pregnant or being HIV positive. The test detects specific components in the blood which indicates that the person has the given disease or condition. The tests are cheap and easy to administer. Sometimes, however, the result is a false positive. The test, and a false positive means that the test gives a positive, but the person does not have the condition. Or you can get a false negative, right? That's where you get a negative when the person actually has the condition, does not have the condition. Okay? So there was a headline, and it says, here it is. It's about the ELISA test. In detecting HIV, 99 out of 100 people with a positive test do not have HIV. Okay, would that be really unsettling if you got a positive result for HIV? Yeah, not as unsettling as it was when I was in high school in the 80s, right? Because we have all these great treatments for it. But 99 out of 100 people, right, get a positive test, but they don't have HIV. That makes for a real horrible test, doesn't it? Right? But that's a claim. So let's see if the claim is true. So what does that mean? Well, I just described that. So let's skip that and move to the next. So at the time of this headline, the test was expected to be positive in virtually all cases where a person was infected. Okay, so you expect to get a positive result. The rate of infection was approximately 1 per 10,000 people in low risk groups who were tested. So this 10,000, right? That's going to be this part here. So again, we're not doing a 1,000 two-way table. We're doing a 10,000 one, right? We're going to work with the actual data. But notice this here. They are giving us a piece of information that's important here, and it's the rate of infection was approximately 1 in 10,000 for people in low-risk groups who were tested. So, well, that is going to be persons that actually have HIV. That's going to be right here. So I can put this information in. That will be 1 in 10,000. Notice here, they also gave us a second piece of information. Overall, the test was 99% accurate. Overall, the test was 99% accurate. So that means so I think what is helpful here is this. Okay, so I'm going to take this information and we're going to interpret this just a little, because if it's accurate, right, that means that when it's a negative, you're negative, and when it's a positive, you're a positive. Does that make sense? And so you have to kind of break that up over two. Or we can say that 1% inaccurate. Do you agree with that? So 1%, that's 0.01, right, of the 10,000 is 100. So that means that these two, right, that's when it's inaccurate, have to add up to 100. Now, there's a given in this next one that we should look at. So notice here, let's skip that question. It says complete the table and the tree diagram to analyze the figures for a random sample of 10,000 people tested, which I already put that number in, assuming that there are, notice here, no false negative results. Okay, so that all negative results do mean that the person is HIV negative. So that gives me this piece of information right here. A negative results means that the person actually is negative, and so means none of them will be positive. So that gives me here, this is 0. Oops. So we can fill in this cell right here because we know that this is going to be 9,999, right? Because these have to add to be 10,000. And we know this one has to be 1 because these two cells have to add to be that one. Okay, and I did just say that these two cells, right, are the 100, right? This is getting a negative result when you're actually positive, which we said was going to be 0. And then this cell is getting a positive result when you're actually negative. So that means all of this 100 here is going to go in this location. Does that make sense? So I know this is going to be 101 when you add going down. I know that if I add going across here, that this cell will be 9,899, which means this has to be 9,899. So, and then let's just write a note because I want to be careful. So for these two cells, technically these two have to add to 100. Okay, so with that, let's come here. It says, what is the probability that a person with a positive test result is actually HIV negative? So we're going to look here for the probability that you are HIV negative, given that you got a positive result. That's not what you want, right? You don't want to, if you do not have HIV, you don't want to be told that you have it, right? Does that make sense? So what is that probability from the chart? And so if we are looking at the chart, remember we are given, let me use let's highlight the given, which is positive. So a positive test result means we're going to focus just on this column. And so if we're focusing just on that column, the total for that column is 101. And how many of those are going to be, of those 101 are HIV negative? And that's 100 of them. And when you do divide that, you're going to get approximately 0.99. Okay, and isn't that the 99%? Okay, are we good with that? Yeah? Now, so that justifies that heading, that statement, doesn't it? 99 out of 100 people with a positive test does not have HIV, right? So the question is, it says here, note, there are other HIV tests available which can be used to confirm the result of an ELISA test. This would not be the only test used where there was a positive result or a real concern about that a person might indeed be HIV positive. So why is this test helpful? Looking at the data, right? Why is this test helpful? Say that again. Okay, yeah, they're cheap and easy to administer. Okay, that's good. Why else? It is one of my reasons. Look at the data. What were you going to say? There's no false negative, right? So I was going to put this as my number one reason here. I actually have a couple. And so a negative result is HIV negative. So if you were to look at the chart, right, probability of HIV negative, given that it was a negative result, if I look at my table, right, given a negative result, right, if you are HIV negative, right, it's 9,899 divided by 9,899, right? Okay, that's 100%, isn't it? So better put, let's write it this way. 100% of negative tests result is HIV negative. Got it? So the second thing that I would state here is to remember the ELISA is looking for a bunch of things in one test. Okay, so think about it, right? I think they even said pregnancy was one of them, right? So if a woman is going in and they want to test for pregnancy, and she thinks she's pregnant, so they want to test that. And then while they're doing that, they can test, right, other things, including HIV. HIV is a blood-borne, it that's how it transfers, right? So obviously that would be a concern for someone who is pregnant. And so where this is nice, right, you could get a positive result that you're pregnant, right? And then you could also immediately get a negative that you don't have HIV, right? If it comes back positive that you have HIV, are you going to trust that are you going to is the doctor going to tell the patient that they have HIV? No, but they're going to say, we'd like to do additional tests, right? To just test for further things without going into probably details at that point. Does that make sense? But do they need to test further if it's for HIV if it's a negative? That's the big thing, right? And remember, these tests are cheap, right? Which is why they do it. So I'll just write here a negative test result. I'm going to do some abbreviations for the sake of time. A negative test result means you don't have to investigate further. I'll write HIV further since that's the context, right? But a positive test result would mean that you'd have to investigate further, okay? I'll leave it there, but I'll just put it in words, okay? And I'll wrap up the lesson there.